Now let's do this CSTR in series. We've seen single conversion and global conversion, so you have no idea of what I'm talking about. Please go to the previous video because it's very important. Now, let's say we have this system. We have an inlet, and we have this tank which has a conversion of 0.4, and then you take it away, FA of 1, this is my outlet, which is the same inlet to the reactor number 2. And until here I have a global conversion of 0.8. This means that this reactor has a random, let's say, conversion of number 2. I don't know it, but I know that the whole process is here at 80%. And I have an outlet here. Now let's do the mass balance here on number 1. It's the flow going in minus the flow going out plus the generation equals the accumulation. So we have no accumulation because it's steady state. The inlet of my first reactor is this one. The outlet of my first reactor is also this one. My generation is this one because it's a CSTR and no accumulation. I'm going to substitute this data here. Where do I get this equation? By definition. You know that the outlet stream equals the inlet stream times the difference on the conversion. And I just do some math and I get this value, which probably is familiar to you because it's the first reactor. There's no problem, you have no reference in global conversions or whatsoever. The problem comes when you do the mass balance in the second one. So the inlet now, let me show you, will be FA1 and the outlet will be FA2. So let's put it here, FA1, FA2, plus the rate of reaction and the volume of the second reactor, of course. Now by definition, once again, f of A2 equals f of A0 and the difference. Look how it's not x1, it's x2. So I substitute this data here, do some math, and where is it? Yeah, here I take away this, and then I get along these two, and it's similar, it's just a difference. Which is kind of interesting because now you're telling that you have a reference point, which is the last conversion. So it's not only the second conversion, you take away the first conversion. It's similar because we use and reference everything to f of A0. Also you use a rate of reaction here, dividing, and you got this, let's say, conversions factor here. I got a conversion factor which is a subtraction here and a conversion factor which has no subtraction, and the volume. Now it's very important that the rate of reaction in number 1 is valued at the first conversion, and the rate of reaction of this second volume is valued at the 80% conversion. Yeah, that's everything in theory. Now let's do an applied problem. Comparing volumes of CSTRs in series. Now, you could either buy a huge CSTR or buy 2 medium CSTRs. We want to see what is better. We're going to use a CSTR to get 40%. Okay, this one is going to achieve 40%, and the final is going to be 80%. Okay, this is going to achieve 80%. Okay, they give you this table, conversion versus this, which is cool. And the first tip is calculate the first volume of the CSTR, which I told you before is the same formula we've been using so far. Now the second tip is calculate the volume of CSTR number 2, which is not that easy because we need to apply this one here. The trick here is to remember this. I know that plugging the numbers is easy, but the thing is knowing what to do. Okay, so let's do it. For my CSTR1 is this equation, my volume 1 equals my inlet flow times my conversion divided by the rate of reaction at this percent. So let me go find out this here, which is in this table. At 40% I got this. I got my x and f of a divided by minus r, which is nice because I already have it here. So if I want to have this f of r, I will need to find f of a and my rate of reaction here. But I do have it, so I use the whole number, which is 2.05 times the conversion, which is 40. So I use these two numbers and I get this value for my first reactor. Now let's go back. We're going to use the one of 80% here. So volume 2 is essentially inlet flow times the difference on conversions divided by my rate of reaction at 80%. But I don't have only this, I have this whole package, which is cool because I have less operations to do. So let me go back, and yeah, 80% implies 8 here. So I get this along, I know it's 8. So 8 here, and the difference on conversion, so 8 times 80% minus 40% gives you 8 times 40% or 0.4, which is 3.2. And if you wanted to know the total value, volume will be volume 1 plus volume 2 at these guys, and it's around 4. So if you hopefully remember, let me see, yeah. If you remember the CSTR exercise we just did, like, I don't know, maybe 3 or 4 videos ago, for the same conversion, same conditions, same reaction, I got 6.4 cubic meters volume. Now for this new arrangement, I got 2 CSTRs. One goes to 40% and the second one goes and finishes also in 80%. And we need now, with this arrangement, only 4.02 cubic meters, which if you see, if you reference it, you will need 50% more. Or if you reference it to this one, you will need 30% less volume. Now the question will be, is it worth it? The reactor sizing is not the only factor to decide. I told you before that we're only interested in volume, but in real life you know that there are many costs. For example, it's easy to say, okay, let's change the reactors, but look how many trucks you're using, and probably you're paying for that. And imagine you need I don't know, to move that, you need to build that, to construct it, design it, and install it, operate it. So it's not that easy just to say, okay, just change the arrangement. There are many other stuff that you are going to see in your other courses. Now I would like you to try at least 3 one. So I have always wanted to know all the cases, so this is a special case. How would you use this case? How would you reference it? And yeah, why not more, 4, 5, whatever. So if you want to see more examples like this, go to the web pages here, go to the courses, and go to Reactor Engineering. I think I'm going to do this in another video because it's also a very important topic. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos, or if I should be changing something, or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.